Good morning. Thank you for being here. I'm so pleased to be the lecturer this morning in this beautiful place that I'm visiting, as Jordan said, for the first time, and as part of a series on wonder and awe, which I think defines a lot of my scientific career and possibly a lot of my personal journey as well. I will tell you quite a bit about how we embarked on the black hole imaging project and some of the early work that I have done to define the experiment. But I also want to tell you a little bit about my personal journey in search of wonder and awe. And let me tell you, it did not start with black holes. It started with something much, much, much smaller than that, when I was much, much, much smaller than how I am right now. And to just guide you through that early amazement with science that I've had, I want to share with you that I was a math whiz when I was in elementary school. I already knew that I loved math, I loved using math. And then in 3rd grade, my parents bought me a science encyclopedia. It was, I still remember it, it was burgundy with gold letters. It was thin, it wasn't even something that big. And as I was flipping through the pages, I saw this. It was the picture of an atom. And it showed the nucleus, it showed the electrons according to the quantum mechanical model, the Bohr model of the atom, in orbit around that nucleus. And it said these are the building blocks of matter. And even then, I remember, I was thinking, why do we have the shapes that we do? What holds us up? What is smaller? What is smaller than cells, smaller than things that we can see? And I saw this, and I was immediately hooked. From that point, I was probably 9 years old, just 3rd grade. And from that point on, when people asked me, what are you going to be when you grow up? I said, atomic physicist. There was no hesitation. So then you're going to say, you're studying black holes. There is a small and a big problem here. What happened? Well, I did spend a lot of time studying atoms. I went through my undergraduate years at Columbia saying I want to do particle physics and I want to understand what is at the building blocks. And when I say building blocks, it's not just the nucleus, that's the neutron and the proton and the electrons around it. We want to understand what is interior to that. What are the most fundamental particles that come together and make up everything that we see in the universe? So I started working on quarks. I started working on theories that are called extensions to the standard model of particle physics. And after my undergraduate degree, I went to CERN for a year, thinking that that's how I'm going to continue my career. And why CERN? Well, CERN at the time had one of the biggest particle colliders in the world, and this is one way to study what is the subatomic structure. What you do is you speed up these particles as much as you can with magnets traveling around a circle, and you smash them into each other, and you look at what comes out. And what comes out rearranges itself differently depending on what the inner constituents of those particles are. This is actually called a jet, a shower of particles, when two of these accelerated, at the time, electrons and positrons, now protons and antiprotons, collide in the middle of a detector and create this shower of particles that you're seeing on the screen. However, this was late 90s. The Large Electron-Positron Collider was about to shut down, and there was going to be a 15-year gap between that and the Large Hadron Collider, which we now know is operating there, would come on. It just wasn't the right time to be using this tool to get at the question that was burning me. What is the smallest constituent of matter, and how does matter behave at those extreme conditions? So I pivoted. It was basically a different way of formulating the question that I was after, that I wanted to answer. And I realized that the universe actually provides a laboratory by which we can study these questions only if we formulate them a little bit differently. Why necessarily have to speed up particles and smash them against one another when there are places in the universe where gravity does that for us? Gravity is the other force that, of course, makes the planets move, makes us stand firm on the ground. And at its extreme, there are places in the universe where it actually is so strong that it smashes particles together for us and makes the densest form of matter known in the universe, called neutron stars. So on the left, what you see is a cartoon representation of a star that used to be maybe 10 times the mass of our sun. And at the end of its life, when it ran out of fuel, gravity took over and it condensed it into something so small that it is now about 20 kilometers across, about 13 miles across. It is fascinating that you take all of that matter that used to be several suns and you squeeze it down because of the strength of gravity, and you make the densest form of matter known in the universe. So instead of working on particle colliders, I formulated the problem as, okay, what are the properties of neutron stars that allow us to study what happens to matter at those extreme conditions? As I got more and more into astrophysics, I actually realized there is a related, very interesting question. In neutron stars, the matter can withstand the gravity. And ultimately, even if it's dense, even if it's some new form of matter, it is still matter. It is still particles to speak of. It still has a surface. It still has a size. There are situations where gravity is even stronger than that, and it wins over in a way that condenses everything into an infinite point of energy. And those are black holes. So there is this invisible line in the universe where if particles can withstand gravity, you get these amazing objects called neutron stars. And if gravity wins over, even past that point, beyond that invisible line, we get what we call a singularity, an infinite energy density. Not only that, but not only is it not matter, but it behaves in ways that are so strange that even though it was Einstein's theory of gravity that we call theory of general relativity that predicted the existence of these things, a mathematical solution, he spent his entire life fighting it. He said, there's got to be something different that stops this from happening. He actually was not a believer in black holes, even though it was the natural consequence of his own formulation of gravity. So, do these things exist? Are they singularities? Are they these extremely weird, surfaceless, infinitesimal objects that not only don't have matter, but start swallowing things that are beyond them, beyond what is called their event horizon, that point of no return. So science is part awe of what you see, and part formulation of the next question. You have to be able to design an experiment that will give you a quantitative answer to, is this the way this is happening? So the next stage of my life, I designed 3 questions on neutron stars, aimed at understanding particles, on that dividing invisible line between where you cross that threshold, and on black holes, on are they singularities with event horizons. I'm going to not talk about all 3 of these. I'm just going to focus on the last one going forward. And the reason is that it shows physics at its most extreme. So I said it swallows things around it. Why is that? Well, I said our formulation of gravity is called theory of general relativity, that actually says that anything with a mass curves the space-time around it. So if you think of space-time as some kind of a fabric, our sun curves the space-time around it. Our Earth does. You, I. To varying degrees. Our mass is small, so the curvature around us is small. But we interact with the Earth's gravity because of this curvature. What is special about black holes is that this curvature is so strong, so if you dropped a black hole into this fabric of space-time, and you started shooting light rays, the light rays would not travel in straight lines anymore, but would curve around that fabric that has been distorted by the presence of the black hole. And as you can see, even though we are shooting parallel rays of light, parallel paths, some of them curve so much that they are trapped by the presence of the black hole. That is that event horizon that our theories say must be there. So we wanted to understand how we can actually see this happen in nature, this point of no return, the darkness at the center, and that took me to the formulation of the question that led to the Event Horizon Telescope. At this point, I was in graduate school. I was at Harvard working on this problem pretty intensely. And one of the things that we needed to do was understand what are the nearby objects or sky objects for which we can see this phenomenon. How do we set up the experiment? What wavelength of light do we look in? Do we look in where we can see the optical? Do we look in X-rays? Do we look in radio waves? What will allow us to see through everything else, see through the gas swirling around the black hole on its way in, and actually get to the heart of this shadow that we say is happening? So I just want to briefly flash to you those early results, even though in public talks I don't really like to show a lot of graphs. I want to just draw your attention to a couple of things from these 2 papers that I wrote as a graduate student in 2000 and 2001, and that is the formulation of where we should look and how we should look. So these 2 graphs are basically telling us, as you can see on the left, there is a label on that graph that is SGRA star. That is shorthand for the source at the center of our galaxy, Sagittarius A star. It's towards the constellation Sagittarius. That's where the center of our galaxy is. And it is a well-known faint source that we've suspected, for reasons that I'm going to share with you, harbor a black hole. And so Sagittarius star, as we call it, was one of the black holes that I said, you know, we should be able to see this point of no return if we look there. And furthermore, we should be looking at a wavelength of light that is the millimeter wavelength. And on the right, I identified the second source with a colleague, M87, which is the second black hole that we targeted, which is in the Virgo cluster. It's not the nearest black hole by any means, but it is so massive that it looks big in the sky. So we started formulating an observational strategy that is based on that. So these are the Sagittarius star and M87 targets. Just to share you some pictures, that's my desk at Harvard in 1999 when I was working on these pictures, on these papers. And on the right, actually, my collaborator since those times and my husband, whom we moved to the Institute for Advanced Study with together. And we just shared a lot of this early development of how do we get at these questions in our joint work together. So, do you know what this is? The Milky Way. Yes, this is our galaxy, the one that we happen to reside in. It's one of the most beautiful ones, though, I have to say. And this is showing the center where Sagittarius A star is. And I already mentioned that we had an inkling that there was a black hole residing at the very center of our galaxy, Sagittarius star. Why did we think that? Well, there were already almost 2 decades of observations, but not in 2020, but not in 2000, but by 2020, that showed us a very strange behavior of stars around the very center of our galaxy. So I have this nice movie of actual images. In this talk, I'm going to also show some simulations that we produce on computers. But this one is actually stitching together of images until the very end, where it will switch and show you the orbits of stars. So if you were able to have the superpower of traveling through the galaxy, through the clouds of dust and gas and stars, and if you were able to switch also the wavelength your eyes see from optical to infrared to whatever was necessary, what you would see is that there is a cloud of stars at the very center that are orbiting around an object that is 4 million times the mass of our sun. But it's basically black. It just shows a little bit of light that our telescopes can pick up on. If it was something like a star, it would be many, many trillions of the brightness of the sun. So it would be the brightest object in our galaxy. And it certainly is not. So because our telescopes were able to follow the paths of these stars over the years, just like planets orbiting around the sun, they're orbiting around something. It's just that that something is not a normal star. That's why we had the inkling that this was some dark object, and it was a black hole candidate. So we have Sagittarius star, we have M87, we have that early work that said, here's what we should look at, here's what we should look for, here is the wavelength that we should look at. Excuse me. There was just one problem, which is that these objects weren't exactly big. Even though they are big, very massive, they are so compact and so far away that they look tiny in the sky. How tiny? So this is the moon. The moon is half a degree across when it's a full moon. So let's take that degree, 2 moons, and divide it into 60. That will get us a unit called arc minutes. Keep dividing. Arc seconds, 1,000 milliarc seconds. Divide that into 1,000 to get microarc seconds. So the predicted size in the sky of Sagittarius A star was 50 microarc seconds. Okay? So 100 millionth of a degree. Not exactly something you can take out a backyard telescope and look at. Okay, so how small is that? I mean, I know I went through the math, but really, how small is that? If you put a donut on the moon and then said, take out your cell phone and take a picture of the donut, that's how small that is. So basically a fool's errand, but we didn't give up. We said we can develop the methods, we can develop the technology to make this happen. What we needed was a very, very large telescope, because a telescope's resolving power, its ability to see fine structure or small objects in the distance, scales with its size. So on the left, that is more of a backyard telescope. On the right is the biggest single-dish telescope that we are building right now as humanity. It is called the Giant Magellan Telescope. It's going to go to Chile, hopefully, when it's completed. And these come nowhere near what we need. Okay? They are orders of magnitude off from what we need. So instead, what we did was utilize a technique called very long baseline interferometry. If we can't make a single telescope dish that is big enough to resolve the small detail of Sag A star, what we could do is take telescopes at different parts of the Earth, look at Sag A star at the same time, record the data, and then use supercomputers to combine the data to make it appear, physics-wise at least, as if we could resolve the distances that are separated by those telescopes, as if our telescope was as big as the separation between them. Okay? This is a technique that has been developed in astronomy. And what makes it very long baseline is that the telescopes are so far apart that you can't run a cable between them. You have to do what I just described, which is record petabytes of data. You heard that, petabytes of data. And then combine them on a computer after the fact. Okay? So it took many years, about 15 years from those early ideas until we got to a global array of telescopes, a global network of telescopes that could talk to each other. Okay? They all had the hard drives, they all had the exquisite timing capabilities, so we knew exactly when the light arrived in each. And we were able to collect the right wavelength of light and combine it and look at it together. So over the years, until our first global campaign in 2017, we spent a lot of time my colleagues, I'm not an instrument builder, spent a lot of time building machines and instruments and connection capabilities for these telescopes that spanned the entire globe, from the South Pole to Greenland, from Hawaii to Arizona to Mexico to the Chilean desert, to the Alps. And all of these telescopes could talk to each other in the way that I just described. We also started from a handful of people on this crazy journey. And by 2018, when we were working on the first analysis, we were a team of about 200 scientists working on both the theory and the instruments and telescope operations. So I'll just show you a few more. I love these telescopes. Like I said, I'm not an instrument builder, but I just truly appreciate the window on the universe that they open for us, the exquisite data that they can collect. And just even if what comes out of these telescopes on its own is not enough to answer the questions that we want, there is just a sense of wonder that comes from the data from each one of these telescopes. I spent a long part of my career at the University of Arizona, so the one that I'm most familiar with is this telescope on Kitt Peak, and another one in a nearby mountain peak in Arizona called Mount Graham. It's called the Submillimeter Telescope. These are two of my colleagues at the University of Arizona who spent a tremendous amount of time building instruments for not just the Arizona telescopes, but also for the South Pole. In fact, the one that you're seeing here, covered in gold because of its wonderful thermal conduction properties, got transported to the South Pole telescope through their years-long effort. They traveled in cargo planes, they made their way down to the pole multiple times, and of course, took part in run races, run around the world, which involves just circling the South Pole. They had fun. And by 2017, our team was ready to take the first set of observations on each of these telescopes simultaneously. We prayed for good weather. We got good weather, even though millimeter wavelength of light doesn't care that much about sunlight. It cares about moisture in the atmosphere. That's why we built these telescopes in high and dry places, like mountaintops and deserts. And our first set of observations went really well. And here we were in the control center in Cambridge, Massachusetts at the time, waiting for the data to come in, and each day deciding whether every telescope was ready for that day's observation or not. Because we needed the whole array. It wasn't sufficient to have one telescope here, one telescope there. We needed all of them to contribute. So, I'm not going to show you the results. The reason is that I started out by asking a question. I said we formulated an experiment, and I described to you one path that we took, which is what it took to get the telescopes ready. There was a parallel path that I was walking on, which is what did it take for us to build analysis tools and theoretical tools that would allow us to turn those voltages from telescopes into a scientific answer. And that's what we spent the 20 years on. And initially, when we started, we were doing simple computer models. And why do we need a computer in the first place? The reason is that the problem ends up being quite complicated. A black hole is a mathematically simple object, but you put it in the real universe, and it does all sorts of crazy things. It breaks apart stars that come too close to it. That gas swirls around it in a hot plasma, and it slowly makes its way down to the black hole. But in the meantime, shines, because it's a hot gas, it shines some light. And that's the only time you can actually glimpse that light. Once it crosses that event horizon, remember, we are not supposed to be able to see it. So we had to build computational simulations that took into account how the gas moves, what does the black hole do, what happens to light once it's produced by that hot gas. Does it come to our telescopes, or does it make its way into the black hole and disappear forever from the observable universe? So these ended up being sets of really complicated equations that we needed computational power to solve. We worked on that, and we realized that traditional computing methods, this is now around 2010, were not going to get us to where we wanted to go. So our group at the University of Arizona started bringing GPUs, graphic processor units, into scientific computing. Now GPUs are at the heart of all the AI models that we are finding out about more and more. But this is 14, 15 years ago. It wasn't the norm. It was a new computing architecture, and we had to work on ways to adapt them to solve scientific problems instead of just being useful for video games, which is what they were designed for. So I'll show you a little video from those times. This is my former student and postdoctoral fellow in the group, C.K. Chan. What he's going to do here is run one of these complex computer simulations, 1 million paths of light, all at the same time. And he's going to run it on his computer on a single GPU and control the entire simulation with his hands through a leap motion device that you can see right at the lower, just under his wrist. You can see it in this video. So here's what it looks like. He is integrating the equations forward, so all those paths of light interact with the black hole at once. He can run it forward, he can run it backwards, he can zoom in, zoom out, he can change the orientation in real time, solving Einstein's equations for how light moves through this medium for 1 million particles. So this was a game changer. It took us from our early predictions and our early analysis tools to what we needed in order to understand what we're seeing in the black hole images. So we were able to map a black hole with its hot swirling gas around it to images that we would see on our computers, which is the upper right-hand part of the screen, where you're seeing a snapshot of this is what it would look like. Okay? So that was on a single GPU. That certainly wasn't enough, but when we showed the proof of principle that this was a fruitful way to go, we were able to get support from the National Science Foundation and build a cluster of GPUs. At the time, the only one in a research university in the entire world. And here's a picture of me from 2012, proud with my baby. And we then were able to start running very large-scale simulations that were a game changer. So, for example, I claimed that the millimeter wavelength of light, according to the early calculations in 2000, were the right place to look. Now we could actually produce graphics like this, actual simulations like this, that showed that as you change the wavelength of light, you go from seeing the cloud, the torus, all the way down to the horizon. And not only that, but if you had the time resolution, you could also see the gas moving around the black hole in our observations. We didn't stop there. We built an entire simulation library, asking tons of what-if questions. What if the black hole is bigger? What if it's smaller? What if it's spinning around its axis? What if it's not spinning? What if the magnetic field around it is structured? What if it's tangled? What if the gas is coming at a higher rate than what we think? What if it's coming at a lower rate? What if we're looking at it sideways versus face-on? We asked so many what-if questions, thanks to this network of simulations that we were able to build, that we made galleries of those. These are all, each one is many, many days of computing time on superclusters that are asking these what-if questions, because that's the only way you can get at a quantitative answer to, is Einstein's theory right? Is it really producing a singularity? And is it going to show us some deviations once we get this image from the telescopes from what we expect to see? So these allowed us to build tools to measure the properties of the black holes. This is very simplistic, but we basically needed to know how much light we're going to see, what the diameter of that bright ring, which we lovingly call the donut, is going to be, and how that ties in with what we want to know about the black hole. So that bridge between the visible and the invisible, we were able to build those tools. Now I'm going to show you the results. I was lucky enough to share it on behalf of the collaboration, the first picture of the black hole at the center of the Milky Way in 2022 in Washington, D.C. And the press coverage and the response from the public was truly amazing. We were very, very grateful for that. But we were even more grateful for the memes. Our orange donut. I think we called it a donut way too many times. So, joking aside, this is our black hole. This is the black hole at the center of our own galaxy, the Milky Way. Thank you. It's a work of 200 people over 20 years. Let me just emphasize that one more time. So, I'll just flash for you, because we spent so much time formulating that scientific question, is this what we expect to see? We saw those stars orbiting a dark object. We knew how massive it was supposed to be. We knew what the theory was predicting for the size of the image. Was it the right size? And here is that result. I just want to show you again the various measurements we made on the part that we could see and how we translated it to the part that we couldn't see, which is the properties of the black hole. And the fact that that purple band is around 0 means that that is what we wanted to see. If the theory was right, it would be in that purple band. And in fact, our measurements were in that purple band. Now, I have to say, we were both very relieved, but also disappointed. That's how science goes. All of that effort to try and answer a question is secretly hoping that we're going to find something different than what we thought. because that's the way we're going to get the next idea about, okay, we have these subatomic particles, we have this immense force of gravity described by general relativity. How do they mesh with each other? Where is that dividing line? Why is there this discrepancy between our theory of the subatomic world and our theory of gravity? We were secretly hoping the purple band would not be where we see our results. But we move forward. We say, at the level of the experiments that we were able to conduct until today, we don't see a deviation from our current theory of gravity or current theory of anything else right now in physics. But we're going to dig deeper. For example, we already started using some new machine learning techniques to sharpen our image, to really build in more confidence to the results that we're reconstructing from this global array of telescopes and from our large set of computer simulations. So the early images and the images that you see on the rightmost is already giving us more sharpened information about the theory that we're trying to test. Right now, actually, my group at Georgia Tech is working on something that's beyond that, not just these machine learning algorithms that we think are going to be fruitful, but we're basically done with what we can do from the ground. We've covered pretty much every continent. We're building a few new telescopes, including in Africa. But that's not going to drastically change what we are able to do in terms of the frontier of science. It's going to give us a little bit more detail, but still on those two black holes, Sagittarius A star and M87. To do significantly better than that, we have to separate the telescopes further apart. And that we can only do if we go to space. So my group right now is working on a mission concept, an early mission concept, where we would put telescopes in orbit around the Earth, past the geosynchronous orbit, and still be able to coordinate the data that we collect between them. There are a lot of challenges. I talked about collecting petabytes of data on the telescopes on Earth. We would still need to do this in space, and we would need to be able to handle that volume of data. We would need new analysis tools. We would need to understand what other black holes we are able to target if we build these new telescopes in space. So it's a new effort. It's one that I'm very excited about. That's where my career is taking me now, from particle colliders to computers to now space missions. And I'm very excited about what the next 20 years is going to bring in terms of exploring the universe with these tools. So before I conclude, I just want to tell you a little story just from last week, not from my scientific life, but I was lucky enough to take a week-long vacation with my family just this past week. And we were by a beach, beautiful, clear sea. And I had my little goggles on, not even a full snorkel or anything, swimming with my two daughters who are pretty grown, 18 and 20. And at some point, my 20-year-old said, "Mom, you're like a little kid. You can entertain yourself for hours." So I stopped and I thought, what a wonderful observation. I can entertain myself for hours. I was counting the types of fish that we were seeing. I was looking at the waves breaking and thinking of wave theories and how much the height I wish I was kidding. I'm not. And then the waves leave particular patterns in the sand. I had a colleague who ran experiments on what sets those patterns and the wavelength between them. I was looking at that. I was looking at how the light comes in and reflects off of the different depths at the sea, because you know that's what I do for a living. So I said, well, thank you. That basically tells me I've never lost that sense of wonder. And I am a little kid. And my hope for all of you is that neither do you ever lose that sense of wonder when you look at the world around you, the nature, the space, whether or not you have the mathematical tools to go to the, what's the wavelength that it sets? Doesn't matter. I hope that you all look at the world with a sense of wonder going forward. Thank you.